Caution: trees obscuring view of forest. Unsupervised machine learning. In this unit, we will look at a very interesting problem, the problem of clustering. To simplify, this is how we divide an assortment of data points into only a few groups. It is one of the most basic problems in unsupervised machine learning. When working with a dataset comprising many data points, we often lose our ability to see the forest for the trees. Now, I don't necessarily mean seeing them visually. That can be also true. But what I really mean, seeing the main elements in it, spotting what is worth knowing about, understanding the big picture. Certainly, these are all high-level, maybe even ambiguous definitions, seeing the main elements. Many times, these are the kind of things we would like to see in datasets, even before we start calculating the solution for a certain question, sometimes even before we phrase the question to ourselves. This is the very essence of unsupervised machine learning. What can the data tell us about itself? What is encompassed within the data? Well, one of these things is the data comprised of clear subgroups? What clusters of data points can be found, and what defines these clusters? Let's look at a medical example. Assume this dataset is a certain slice from our EMR database of patients with features of a metabolic syndrome. For each patient in this example, we measure 10 different variables, as you can see here. According to the rationale of personalized medicine, we assume that every patient is different. However, naturally, we can also assume that these patients do share some similar biological characteristics that are related to their metabolic syndrome. So, well then, are they different or the same? Usually, none of the above. The comedian Carl Waxman once said, "Even if you are 1 in a million, there are 7 more of you in New York." Mr. Waxman did not mean that you have 7 identical clones of yourself, but rather, out of the millions of people in New York, there are probably a few people who are very similar to you according to certain parameters. Now, in biology, the situation is similar. Out of the billions of people in the world, out of the billions and billions of molecules that compose each person, we can safely assume there are always archetypes that could be found. Of people, of diseases, of biological conditions, whatever. So the two extremes of this spectrum are probably wrong. People are not the same, but also not entirely different. No 2 people with the same disease are identical. However, they may be very similar according to certain parameters. On the other hand, other 2 people with the same disease could be significantly different according to these exact parameters. The notion of having archetypes is very natural, very fundamental, and highly connected to the biological, biophysical, even genomic mechanisms that create and affect life. Let's see if we can spot these archetypes in our dataset. Let's plot all these patients in a chart. Considering we cannot see more than 3 dimensions, let's pick, just for the example, potassium, white blood cells, and salary. Voila! We definitely see that our patients created 3 groups. Well, it's not really that they created groups, but probably that the medical condition is manifested in the population by 3 different archetypes, at least in terms of potassium, white blood cells, and salary. It's good to know that. Clearly, insights from actual patient data about how this condition is manifested are interesting, allowing us to further research and discover the underlying biological mechanisms that are the root cause for this distribution in the population. Eventually, we may want to treat each archetype or group of patients differently. That would become the basis of personalizing medicine. In the next segment, we will dive deeper into this problem from a more concrete computational perspective. This is usually when things start to get tricky.